Calcium is a pretty surprising element when you get to know it. On one hand, it's an unassuming mineral we associate with healthy bones, milk mustaches, and chalky antacid tablets. On the other hand, wait for it, calcium is actually a metal. Yes, a shiny silvery metal that fizzes in water and burns with a red flame. In fact, if you drop pure calcium into water, it reacts and releases hydrogen gas, which can even ignite. So given that our bones contain a lot of calcium, and our bodies are mostly water, you might jokingly wonder, shouldn't our calcium-rich skeletons explode or catch fire whenever we go for a swim? Thankfully, the answer is no, and the reason why reveals a lot about the chemistry of this remarkable element. Welcome to Cube Chemistry, where we will discuss all the elements of the periodic system and also do experiments. If you like this video and want to see more, make sure to hype, like, subscribe, and hit the notification bell so you will never have to miss another episode. Also, thanks for a great year in which the channel grew more than we could have ever hoped for. Have a great New Year's Eve, and speak to you in 2026. Now in this cube we got calcium in its pure elemental form. It looks like a pale silvery gray metal. It has a soft, almost waxy sheen when freshly cut, with a surface that can gleam faintly under light. It feels relatively lightweight in the hand, not dense like iron or copper, and has a slightly chalky texture once exposed to air. If you would take it out of this cube, it would quickly lose its shine, as a dull white or grayish crust begins to form, almost like a thin frost or dry film. It might remind you of lead or aluminum, but it's a bit brighter and more fragile looking. The surface feels dry, a bit rusty, and unassuming. Nothing about it screams danger at first glance. It looks like something you might mistake for a soft piece of metal or a chunk of dried mineral. So yes, well, it is the last day of the year, so would it be a good day to lick calcium? No, you should definitely not lick pure calcium metal, and I'm not sure why the periodic licking table is even remotely suggesting that it wouldn't harm you. It reacts with water, and that includes the moisture on your tongue. This reaction produces calcium hydroxide and hydrogen gas, which can cause chemical burns and potentially release flammable hydrogen. Not exactly a tongue-friendly experience. However, calcium in everyday life, like milk, cheese, leafy greens, or even chalk, is found in the form of safe, stable compounds like calcium carbonate or calcium phosphate. These are not only safe to consume, but essential for strong bones and healthy muscles. So, while the elemental metal is hazardous to touch or taste, the calcium in food is pretty safe and even necessary. Calcium's story stretches back thousands of years, not as pure metal, but in the form of compounds that ancient people knew and used. Long before anyone isolated the metallic element, humans were building with calcium compounds. One of the earliest uses was lime plaster. Around 7000 BC, people in the Middle East were burning limestone, which is calcium carbonate rock, to create quicklime, calcium oxide, and mixing it with water to make plaster. The ancient statues of Ain Ghazal and the Great Pyramids of Giza, for example, used lime-based plasters and mortars. The Romans later perfected the use of lime in construction. They built vast structures like the Colosseum and aqueducts using mortar made by heating limestone, calcium carbonate, into lime and then mixing it into cement. In fact, the very word calcium comes from the Latin word calx, meaning lime. If you've heard the expression in the limelight, that actually has calcium connection too. More on that soon. Now, for many centuries, lime, calcium oxide, and limestone were well known, but nobody knew they contained a metal element. These substances were called earths and were thought to be fundamental materials. It wasn't until the 17th and 18th centuries that scientists began to suspect there was a metal locked inside. French chemist Antoine Lavoisier in 1789 theorized that substances like lime were oxides of some unknown metals. He listed lime as an element in his early periodic table, but with a hunch. He wrote that it was probably an oxide of an undiscovered metal, since no one had managed to reduce it to a metallic form at the time. The breakthrough came with the advent of electricity. In the early 1800s, English chemist Sir Humphry Davy was a pioneer in using electricity to break apart compounds into elements, a process called electrolysis. In 1807, Davy had used a powerful battery to isolate sodium and potassium, shocking the scientific world with these highly reactive metals. The very next year, in 1808, he turned his attention to lime, calcium oxide, following some advice from a Swedish chemist duo, Jens Jacob Berzelius and Magnus Pontine. Davy made a paste of lime mixed with mercuric oxide and zapped it with electricity using a mercury electrode. This clever setup freed the metal in tiny droplets amalgamated with mercury. By heating the mercury off, Davy finally obtained a sample of the new metal element that had been hiding in plain sight. He named it calcium, after the Latin calx, to honor its origins in lime. Thus, calcium, the element, was first isolated in 1808. However, Davy's method only produced minuscule amounts. Pure calcium metal turned out to be tricky to produce in large quantities. It oxidizes so easily and was so hard to separate, it wasn't until a century later that industrial processes were developed to produce calcium metal on a commercial scale. As mentioned, the name calcium has root in the Latin word calx, meaning lime. If that term makes you think of white powder or chalky stone, you're on the right track. Not the green citrus fruit. Lime, quicklime specifically, was an essential substance for making mortar and plaster. Because lime was such a common and important element, the new element Humphrey Davy isolated took on the name associated with it. It's a fitting name considering that calcium is most often found in nature as calcium carbonate, the main ingredient of limestone and chalk. So the element carries a bit of ancient language legacy, connecting it to the construction material that human civilization has used for millennia. Now, we already talked about what it looked like. Let's take a look at some of its other properties. Now, it's relatively soft for a metal. You could slice it with a knife if you press firmly. It's harder than lead, but much softer than iron. In fact, on the Mohs hardness scale, calcium scores about 1.5 to 2. Talc is 1, diamond is 10, so it's pretty soft. It's also lightweight, less dense than iron or copper. A chunk of calcium will sink in water, since it's about 1.5 times denser than water. But it is lighter than many common metals like iron, copper, or lead. One quirky thing you'll notice is that pure calcium doesn't stay shiny for long in air. Expose it to the atmosphere and within seconds it will start to dull. Calcium metal reacts with oxygen and even with nitrogen in air, forming a thin coating of grayish calcium oxide and calcium nitride on its surface. This happens so quickly that you will rarely see calcium metal just sitting out there shiny. It's a shy metal that instantly hides behind a crusty layer of its own making. The oxide layer actually protects the metal underneath to some extent, but if moisture is around, calcium will keep corroding. Now, in dry air, you could store calcium for a while, but in humid air, forget it. It'll start turning into white powdery calcium hydroxide. For this reason, calcium samples in labs are often stored under oil or in airtight containers to keep air and water away. So let's talk about how calcium behaves when it reacts. Chemically, calcium is categorized as an alkali earth metal. It's in group 2 of the periodic table, right below magnesium. Like its neighbors, it has 2 electrons in its outer shell that it really wants to give away. When it loses those electrons, it becomes a doubly positive ion, calcium 2+. This tendency to make calcium reactive, but not as aggressively reactive as the group 1 alkali metals, like sodium or potassium. Still, calcium can do some fun things. For example, which we will demonstrate, calcium and water. If you drop a piece of calcium metal into water, a reaction starts. The calcium will begin to fizz as it reacts with H2O, forming calcium hydroxide and releasing hydrogen gas in the process. The equation is this. The hydrogen gas bubbles out, and the calcium hydroxide that forms is only slightly soluble, so it makes the water turn milky. That's actually the formation of lime water. This reaction is exothermic, gives off heat, but calcium usually doesn't produce enough heat to ignite the hydrogen on its own, unlike sodium, which often ignites. However, if the water is hot or the piece of calcium is big enough, you might see hydrogen catch fire with a little pop or flame. Compared to sodium's violent dances on water, calcium's reaction is more of a vigorous fizz than an explosion. One chemist joked that calcium is about the most reactive thing I'm comfortable letting a 6-year-old handle with a lot of supervision. It's reactive but manageable. Still, it's definitely not a stable noble metal, so if metallic calcium made up your bones, you'd have a serious issue. Taking a shower would be a dangerous proposition then. Fortunately, the calcium in our bones is not raw metal. It's found in compounds, primarily calcium phosphate mineral crystals, which are extremely stable and do not react with water, the way metallic calcium would. That's why your skeleton stays nicely solid and non-explosive inside your watery body. Another interesting property of calcium is how it behaves with heat. If you heat calcium metal strongly in air, it doesn't melt into a puddle easily, it will start to burn. Calcium metal is actually difficult to ignite, unlike the famously flammable magnesium ribbon. But once you get it going, it burns with a brilliant high-intensity orange-red flame. Calcium salts also impart a beautiful orange-red color flame, which is actually used in flame tests in chemistry class, and even in fireworks to produce orange hues. So calcium can literally be quite flashy when it wants to be. In terms of melting and boiling points, calcium melts about 842 degrees Celsius, 1548 degrees Fahrenheit, and boils at around 1484 degrees Celsius or 2700 degrees Fahrenheit. Those numbers are modest for metals, much lower than, say, iron or copper. This moderate melting point, along with calcium's reactivity, means you won't find calcium metal used in high-temperature structural applications. It would just corrode or melt away. Instead, calcium usually does its work as part of compounds or alloys, as we will see. Calcium is all over the place. Quite literally, it's the fifth most abundant element in the Earth's crust by weight. Only oxygen, silicon, aluminum, and iron are more common, and we've discussed them all. Scientists estimate about 3.5% of the Earth's crust is calcium, mostly in the form of rocks and minerals. It's also the third most abundant metal in the crust after aluminum and iron. So if you pick up a handful of soil or rock, there's a good amount of calcium in there, though not as pure metal, of course. The most common sources of calcium in nature are minerals, and we will show a few of them. The superstar mineral is calcium carbonate, which appears in several forms such as limestone, chalk, marble, and calcite. Huge deposits of limestone and chalk around the world attest to calcium's presence. The White Cliffs of Dover in England, for example, are towering masses of chalk, a form of calcium carbonate formed from ancient marine shells. Limestone caves with their icicle-like stalactites and stalagmites are also made of calcium carbonate, slowly deposited from dripping water over eons. And if you ever held a seashell or a piece of coral, you've held calcium carbonate. Sea creatures build their shells and reefs from this stuff, pulling calcium and carbonate ions out of the seawater. Other important calcium-containing minerals include gypsum, calcium sulfate, which forms giant desert crystals and is used to make plaster, anhydrite, calcium sulfate without water, fluorite, calcium fluoride, often found as pretty purple or green crystals, and apatite, calcium phosphate, which is actually what our bones and teeth are made of in crystal form. Dolomite, calcium magnesium carbonate, is another common rock. Wherever you find sedimentary rocks, chances are calcium is a major ingredient because a lot of sediment comes from shells and bones of living creatures or chemical deposits that involve calcium. Calcium is not just a landlubber element, it's also abundant in the oceans. In fact, calcium is the fifth most abundant dissolved ion in seawater, after sodium, chloride, magnesium, and sulfate. Ocean water carries calcium ions that eventually get taken up by the marine organisms or precipitate out as limestone. Calcium's journey through the water and rock is part of a grand geochemical cycling of elements on Earth. Mountains contain calcium, get weathered by rain. River carries calcium ions to the sea. Sea life uses it, and some of it ends up back in rocks on the seafloor. Plate tectonics can even take those sea calcium-rich rocks and push them up as new mountains over millions of years, completing the cycle. What about calcium in ground or mines? Well, we don't mine calcium metal directly from the earth, since it's not sitting around in metal nuggets. Instead, we quarry calcium-rich rocks like limestone, gypsum, and others, and these raw materials are then processed to make lime, cement, plaster, etc. Now, if we want pure calcium metal, we have to extract it from calcium compounds using chemical or electrical means. We'll cover that in the next section on production. Beyond Earth, calcium is also found in space. It's formed in the interiors of stars and scattered when stars explode, supernovae, contributing to the dust that forms new solar systems. We're all made of star stuff. The moon's highland rocks contain a good amount of calcium, mainly as anorthite, a calcium-containing feldspar mineral. And interestingly, calcium gives some prominent spectroscopic lines in the light of stars. Astronomers actually discovered the element's signature in the sun's spectrum. The sun's atmosphere has calcium ions that absorb certain wavelengths, creating dark lines in the solar spectrum, known as Fraunhofer lines. So calcium is truly cosmic, though in everyday terms, we mostly notice it in rocks, water, and living things around us. Lastly, let's not forget about the many places people directly encountered calcium deposits. Your home, plumbing, and kettle. If you live in a hard water area, that scale or chalky white buildup in your kettle or faucets is largely calcium carbonate or calcium sulfate that precipitated out of water. Hard water has extra calcium and magnesium ions that come from groundwater flowing over limestone and gypsum. When that water is heated or evaporates, the calcium comes out of the solution and sticks as scale. It's a nuisance for cleaning, but not harmful to drink, and it's a daily life reminder that calcium is in our water. Considering how abundant calcium in rocks is, you might think it's easy to get pure calcium metal, but as we saw, calcium is very reactive, so it doesn't like to stay in metal form. You can't just melt a rock and get calcium like you could get iron from iron ore. Historically, isolation required clever chemistry. Humphrey Davy managed it with electrolysis on a small scale in 1808, but producing large quantities needed improvements in technology. There are two primary modern methods to produce metallic calcium commercially. Electrolysis of molten calcium salt. This method is conceptually similar to Davy's original approach, but more industrialized. The idea is to take a calcium compound, melt it into a liquid, and run an electric current through it to break it into elements. The most common salt used is calcium chloride because it has a relatively low melting point when mixed with other salts and conducts electricity when molten. Giant electrolysis cells separate the calcium ions, which go to the cathode and get reduced to metal, chlorine gas, which bubbles off at the anode. This process is somewhat similar to how aluminum is made via electrolyzing aluminum oxide, or how sodium metal is made. China and Russia are known to still use electrolytic processes for calcium production. The result is molten calcium that can be cooled into a solid metal, often made into ingots or chunks. Because calcium will react with air, the electrolysis typically has to be done in an inert atmosphere or sealed system, and the molten calcium must be handled carefully. Aluminothermic reduction of lime is the second method, and it doesn't use electricity directly, but rather a chemical reduction. In the US and Canada, a common technique is to start with quicklime, calcium oxide, which is obtained by heating limestone. The calcium oxide is then mixed with finely ground aluminum powder. Now, aluminum is a much more reactive metal in the sense that it has a high affinity for oxygen. When this mixture is heated to a high temperature, around 1200 degrees Celsius, in a vacuum or inert environment, the aluminum steals the oxygen from the calcium oxide. Now, this produces aluminum oxide slag and frees up calcium metal. The reaction can be written down in simplified form like this. Actual products may vary, but essentially calcium comes out and aluminum oxides form. The calcium metal that forms is gaseous at those high temperatures, so it vaporizes. The setup allows the calcium vapor to condense on a cool surface, often yielding solid calcium deposits or crystals in a separate part of the reactor. This aluminothermic process is done in vacuum-sealed containers called retorts, so that the calcium doesn't get oxidized as it is produced. After a batch, you can collect quite large chunks of calcium, dozens of kilograms, from the condensation zone. Any impurities can be removed by remelting or even distilling the calcium again at high temperatures to purify it. Both methods produce relatively pure calcium, but it's not an enormous industry. To give a sense, worldwide production of calcium metal is on the order of a few tens of thousands of tons a year, which is peanuts compared to iron or aluminum production. Once obtained, pure calcium is usually cast into ingots or stored as chunks or granules in airtight containers under an inert liquid like kerosene. If you see calcium metal sold for laboratory use, you'll find it as little tiny pieces submerged in oil. Exposed to the atmosphere, it tarnishes quickly, as we noted. It is worth noting that while pure calcium metal is not ubiquitous in consumer products, calcium compounds are produced on a massive scale. For instance, quicklime production for limestone is a huge industry. It's the basis of cement and concrete. Similarly, gypsum for plaster and drywall, and fertilizers containing calcium like superphosphate, which has calcium phosphate in it, are produced in large quantities. Even though you never see the pure metallic calcium in your life, the world runs on calcium compounds in many forms. Calcium might not get the spotlight like some high-tech elements, but its uses are everywhere, often hiding in plain sight. Let's tour through the many applications of calcium from ancient times to modern days, and from massive buildings to tiny cells in our bodies. So here is how it goes. Limestone calcium carbonate is heated to produce lime calcium oxide. And lime is a key ingredient in Portland cement, the common cement used for concrete, along with silica and other components. When cement is mixed with water and sand gravel, it sets into concrete, essentially reconstructing into calcium silicate hydrates that bind everything together. The Romans used a primitive version of this with lime and volcanic ash to make their concrete, which has lasted millennia. Modern concrete is even more refined, but still heavily reliant on calcium compounds. Beyond cement, calcium compounds are used in plaster and drywall. Plaster of Paris, the stuff used to make wall plaster and orthopedic casts, is calcium sulfate hemihydrate. Mix it with water and it hardens as gypsum, calcium sulfate dihydrate, great for sculpting and casting. Drywall panels, gypsum boards, that make up your walls at home are basically layers of gypsum pressed between paper. So every house or building with drywall literally has walls of calcium sulfate. Plaster of Paris got its name because extensive gypsum deposits were mined in Montmartre in Paris to make plaster. But the use of gypsum plaster goes back to ancient Egyptian and Roman times. Now, mortar is another calcium-based material. Traditionally, mortar for laying bricks was made by mixing lime, calcium oxide, with sand and water to form calcium hydroxide, which then reacts with CO2 in air to harden back into calcium carbonate. If you look at an old brick building or a Roman ruin, the glue holding the bricks or stones is often a lime mortar that has recarbonated over time. It's a neat cycle from limestone to lime and back to limestone as it sets. So calcium has literally been the foundation of civilization's infrastructure. Now there's something fascinating happening in the world of ancient materials, self-healing lime cement. Traditionally, lime-based cements, like those used by the Romans, have a hidden superpower, it seems. When tiny cracks form, moisture creeps in, and the lime inside reacts with carbon dioxide in the air or dissolved in water. This reaction forms calcium carbonate, which gradually fills the cracks and seals them back up. It's like cement that quietly repairs themselves. No glue or patchwork needed. While pure calcium metal isn't used for structural purposes, it does play important roles in metallurgy, the science of metals. One use is as a reducing agent or deoxidizer in metal production. Now, for example, when making certain high-purity metals or removing impurities from alloys, calcium can be added to react with unwanted oxygen, sulfur, or other elements. In steelmaking, small amounts of calcium, usually added as calcium silicon alloy, helps remove sulfur impurities and control the shape of inclusions, which can improve the quality of steel. Another industrial use of metallic calcium is making certain alloys. One important alloy is lead-calcium alloy, which is used in lead-acid batteries, like car batteries. One more interesting industrial application, calcium carbide. Although not a metal itself, calcium carbide is made by reacting lime, calcium oxide with carbon, coke, in an electric furnace. This was an extremely important industrial product in the late 19th and early 20th century. Calcium carbide reacts with water to produce acetylene gas, which was used for lighting carbide lamps in mines and early automobile headlights, and is still used as a fuel for oxyacetylene welding torches. If you've ever seen an old movie where miners have a headlamp with a flame, that's a carbide lamp using calcium carbide. It produces a bright flame from acetylene. Now there is also calcium chloride. Now this is a salt with a variety of uses. In winter, calcium chloride is often sprayed on icy roads and sidewalks as a de-icer because it lowers the freezing point of water and generates heat when dissolving, melting ice effectively. It's also used as a dust suppressant on dirt roads, keeping dust down by absorbing moisture. Good old chalk is basically calcium carbonate, the white sticks teachers used on blackboards, or the sidewalk chalk kids use, were traditionally made of natural chalk, a form of limestone. Modern chalk sticks might be gypsum-based, but either way, it's a calcium compound leaving that white mark. So calcium literally wrote a lot of our lessons until whiteboards took over. Calcium carbonate is used as a filler and coating in paper to make it brighter and smoother. If you have a glossy magazine or a high-quality paper, calcium compounds likely helped it make it shine and opaque. Calcium is involved in making some types of soaps. Calcium soap can be a component of certain detergents or in fabric softeners as calcium stearate. However, calcium in water is what causes soap scum. When hard water is used with soap, the calcium reacts to form an insoluble curd. So while calcium is helpful in many areas, it can be a nuisance in your shower if you have hard water. Most glass is soda lime glass, which, as the term suggests, contains calcium, lime, along with silica and sodium carbonate. The calcium oxide in glass makes it more stable and less water soluble. Ceramic glazes also often contain calcium compounds to give certain finishes. Now, a fun historical application of calcium compound, limelight. In the 1800s, theaters needed a very bright light to spotlight actors on stage. This was before electric lights. They discovered that if they heat a chunk of quicklime, calcium oxide, in a flame, like a oxyhydrogen flame, it produces an extremely bright white light. This was one of the earliest spotlights, and the actors on stage who stood in the intense illumination were literally standing in the limelight. The term stuck around in English to mean being the center of attention. Even though we no longer use actual calcium oxide for stage lighting, it's a neat reminder of calcium's cameo in show business. Many of calcium's applications cross into the realm of nutrition and health. We often think of calcium in terms of diet and medicine. Calcium is a crucial nutrient, so it's sold as supplements. Calcium tablets, often calcium carbonate or calcium citrate. Foods like orange juice, cereals, or plant-based milks are frequently fortified with calcium to ensure we get enough in our bones. The classic source, of course, is dairy, milk, cheese, yogurt, where calcium is naturally high. Just about every Got Milk style ad campaign has played up calcium for strong bones. If you've ever chewed a Tums or a Rolaids for heartburn, I know I have, you are consuming calcium carbonate. The calcium carbonate neutralizes the stomach acid to relieve indigestion, and as a side bonus gives you a dose of calcium. In fact, some people use them as calcium supplement, though regular use should be monitored to avoid getting too much of it. Beyond supplements, calcium compounds have medical roles. Calcium sulfate, gypsum, as a plaster was already mentioned for costs. Calcium chloride injections can be used in medicine to treat certain acute calcium deficiencies or as part of a cardiac arrest management, though that's more specialized. Calcium phosphate materials are used in some bone grafts or dental materials because they can help regenerate bone, given they are what bone is made of. Even calcium alginate from seaweed, but containing calcium, is used in wound dressings to help blood clot and wounds heal. Some toothpaste brands include calcium carbonate as a mild abrasive to help scrub teeth clean and also as a source of calcium for remineralizing tooth enamel. Usually fluoride is more famous for that, but calcium helps too. We often hear calcium equals strong bones, and for a good reason, but calcium's role in biology goes way beyond the skeleton. Let's start with the bones and teeth though, because they are indeed built from calcium. Your bones and teeth are essentially a storage vault and structural framework made of calcium compounds. Hard part of the bone is largely calcium phosphate in the form of a mineral called hydroxyapatite. Chemical formula, something like this. The mineral is deposited on a soft framework of collagen, a protein, which together forms a composite material that is hard yet a bit flexible. Teeth enamel is even harder and is also a form of calcium phosphate mineral, one of the hardest substances made by a living organism. About 99% of the calcium in your body is locked up in your bones and teeth, providing rigidity and strength. An average adult human contains roughly 1 kilogram, 2.2 pounds of calcium in their body, just from all the bone material. Now that's the most abundant metal element in our bodies. We have more calcium than iron, for instance, which might be surprising. Only non-metal elements like oxygen, carbon, hydrogen, and nitrogen outrank calcium in terms of total mass in the body. Now, bones are not static. They're a living tissue that is constantly being remodeled. Calcium plays a dynamic role. Your body can deposit calcium into bones or remove it as needed. For example, during pregnancy, a mother's body will draw calcium from her bones to build the skeleton of the developing baby, which is why getting enough calcium in diet is important during that time. Bones can lose calcium faster than it's replaced, leading to osteoporosis, a condition where bones become fragile. Osteoporosis is essentially a decalcification of bones over time. This highlights how vital calcium balance is in our bodies. But if only 99% of our calcium is in bones, what about the other 1%? Well, that part is incredibly important too, because it's dissolved in our body fluids and inside cells, playing roles in critical physiological processes. Ever wonder how muscles actually contract to move your skeleton? Calcium is the trigger. When a nerve signals a muscle cell, it causes a sudden increase in calcium ions, Ca2+, inside the muscle fiber. Those calcium ions enable the molecular machinery, actin and myosin fibers, to slide and contract the muscle. After the contraction, calcium gets pumped back into storage within the cell, and the muscle relaxes. If there's no calcium, your muscles can't contract properly. Calcium ions are also essential in nerve cells. When a nerve impulse reaches the end of a neuron, nerve cell, calcium rushes in and causes the release of neurotransmitters, the chemicals that transmit the signal to the next cell. In this way, calcium is directly responsible for allowing nerves to communicate. The heart is a muscle, so the same idea. Calcium orchestrates the contraction of the heart muscle cells. In fact, hospitals use calcium injections in certain cases to help stabilize irregular heartbeats or as part of advanced cardiac life support because of its effect on the heart muscle and electrical signaling. When you get a cut, and it bleeds, your body has a clotting mechanism to stop the bleeding. Calcium is one of those critical players in the clotting cascade. Without calcium, blood cannot clot properly, as calcium ions are required to many of the enzymatic steps that lead to a stable blood clot. In blood banks, they add substances that bind calcium to prevent donated blood from clotting in the bag. Now again, Happy New Year to you all, and appreciate the calcium in the fireworks that you may see tonight. Now we would like to thank the members that support our channel. Thanks for doing that. We really appreciate you. Now if you think we missed anything, tell us in the comments, and if you want to know more about another reactive element, take a look at this old video of beryllium next.